This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Non-computer science people seem to like programming computers in ways that make their lives better for some strange reason. And the languages they use, while they offer some benefit to them, often have constructs or execution models that are hard to do well, hard to do correctly and fast. However, often these domains, they're using these languages in areas where if you can run their programs very quickly, there's a huge opportunity for you, despite the fact they're often willing to settle for very slow execution. Today's speaker found such a language and an opportunity, and I think we're going to find that the standard compiler technology does keep winning again and again and again. One thing I'd like to note is that I don't know how many of you use TechMeme, but it's written by Gabe Rivera, who's a compiler guy. So compilers pop up everywhere. Randy Allen has been doing, well, actually this is not the first time that he's done a domain-specific language. It looks like he was doing something with System C at Synapse and other compiler projects involving hardware simulation, which is another place where the languages are not do not look like they're appropriate for fast execution, but can be. Thank you.
Okay.
Now, how do I turn
I don't know,
this
when
off?
I hear the phrase compiler guide in the introduction, right there. Show my age a little bit. This is a quote I remember when I was in grad school. I remember hearing at the time. I'm not certain what the language for scientific computing will be basically now, but I'm sure it'll be called Fortran. And it's interesting. Looking at the time, I swore Bacchus. I've always seen it attributed to Bacchus, but looking through the web doing research for this, I found it's also attributed to Seymour Craig and C.A.R. Hoare, and probably others as well. So this is a technical crowd here. Just out of curiosity, raise of hands. How many people here know Fortran, use Fortran? Okay, more than I would have expected. Well, long ago, oh yeah, well, we had some old timers in here like me as well. How many use C or know C? Okay, doing a little better there. Java? Matlab? Okay, see. So when you see a quote like that, I figure it's either one of two things. Either at the time the quote was made, everyone figured it was such a great quote they wanted to get credit for it, or now that as you look back in the past and see that it's so wrong, everyone's trying to disavow knowledge of it, you know, and be totally disassociated from it. Oh, okay, I'd be.
The scribe at the 1982 NATO Software Engineering Conference, and it is in the notes there. And for the life of me, I can't tell you who said it, but there is a long discussion following it.
Well, for those of you who don't know, Bacchus would be the appropriate one. Bacchus is the inventor of Fortran. But since Bacchus and Cray are dead, I figured sort of one way or another it will get attributed to the you know, either avowed or disavowed by the one guy left remaining. So, I mean, what has happened in 20 years? I mean, you know, in the 80s, it clearly looked like Fortran was going to be the dominant thing, and now it's clearly MATLAB, just from the raise of hands. I mean, what happened in the time frame to cause that? If you look at MATLAB, it really does the type of things that sort of describe the high-level things that mathematicians or that people dealing with very high-level concepts want to do. You know, up at the top is a mathematical expression of a fast Fourier transform. You know, putting a few pluses in or a few crosses in for multiplication that you wouldn't normally put in. But if you look at that, expressing in MATLAB, you look at the two compared to each other, they look very close. It's very easy to look at that and see that it is a fast Fourier transform and relate the mathematics back and forth between the computation and the mathematical expression of it. If you were to look at that same thing written in C, Fortran, or Java, it would not look the same way at all. You'd see 3 loops around there. You'd be figuring out what the loops were. The reduction would be coming in there, making things messed up. So it'd be very hard to see. So first part of it is that Matlab is a language that expresses things where it's very easy to relate it to the mathematics. But they did one step better than that, the MathWorks. They also provide libraries that give you very fast execution of the really important things. So if you want to write your own FFT in Matlab, you can write it in the language coming straight down from the math, or you can just turn around and call FFT and get something that's very highly tuned, very fast, that executes very well. So second part is libraries. Third part is visualization. Not only can I look at it mathematically, not only can I call it in a very abstract fashion, but if I want to, I can visualize it. I can look at the FFT and see it in a visual fashion where I can relate back and forth. So if you look at that, that in my mind is sort of why Matlab is the mathematical language, or the technical and scientific language of the 21st century, and not Fortran. It provides all those facilities, but the really key one is the vectors. If you go back in time, again, it's showing my age a little bit. Fortran 77 standard was actually supposed to have vectors in it. The reason that it didn't was that IBM and Cray couldn't settle on the syntax. They settled on everything else. They were battling back and forth. So what they decided is they'd put off vectors for 1 year, go ahead and get the rest of the language accepted. They'd battle for the year and have a Fortran 78 that would come in and have vectors put in. Fortran 78 became Fortran 80, which became Fortran 8X, which I think finally came out in Fortran 90 as Fortran 90. I got tired of following it about 85 or 86. But the vectors really are a key part. The ability to express the language in a way that relates to mathematics is something that really appeals to users. So if you look at that, I mean, MATLAB's got all those things. What's the key part that's missing? Implementation, in my mind. If you take MATLAB and you want to get to a real product, whether that product is software running on a DSP or running on a processor, whether it's an ASIC, whether it's an FPGA, there's no path there other than working very hard by hand and translating by hand. If you look at the paradigm you see people developing over and over, what you see up here is exactly it. You see the high-level guys, the first algorithm guys starting out doing their initial prototyping, initial development in MATLAB. In fact, the way I've heard it described the best is you got 3 or 4 algorithm guys sitting down at the end of the hall in an office with the doors closed. You slide a pizza box and a sheet of paper saying what you want described or what you want done under the door. Wait 2 or 3 days, the pizza box and a description will come back out, written in MATLAB, or a piece of paper in MATLAB with MATLAB on it. You see that over and over. Initial experimentation or development is done in MATLAB. But at that point, things break. I mean, there's no path, no way to go from there except by hand. So then you'll start seeing people doing the translation to get it down to the implementation. You bring in a group of people that will take that, they'll rewrite that in C code to be able to simulate it. They'll start doing the fixed point quantization, conversion. And so you see a gradual translation. It's all very heavily, where you start out with the algorithm developer, end up with software implementers, start out at a very high-level language that's very easy to understand, and gradually work down to where you get a real product out of that. Again, it's showing my age. You could actually move back about 15 years, and you see exactly the same thing in the hardware development world. At that point, the language would be Verilog. You would see the initial algorithm developers going and writing the stuff in Verilog, getting the things work correctly. Then you would see the gate guys coming along and redoing that in netlist and gates and seeing the verification back and forth. What came in and eventually filled that gap was Synopsys Design Compiler that automated that gap. Made Synopsys, at least in their minds, the most successful EDA company out there. So if you look at the high-level picture of what Catalytic's about, or what we're trying to do, it's exactly that same thing. We believe MATLAB and those languages are the next step up. It's where people are going, and what we want to do is automate that path for those types of things, provide implementation. So in fact, this slide says exactly that. At the very specific or tactical level, what we've seen is people developing the high-level algorithms, mathematical, the representation that you have where you can understand at the human level. They need to get to an implementation, to a deployment level at any number, for any number of possible targets. And they need someone other than humans to provide the path in between. We want to provide that path. We want to be those guys there. Other important part about this is that in our view of the future, signal processing is the way, which is where all these algorithms come from. Signal processing is really the one leading the edge. It's the leading indicator. If you look in sort of all fields, the move to higher level languages, the move to complexity, the ability to deal with complexity is something that people are going to have to deal with. And so what the paradigm that's repeating, that's occurring in signal processing, where you have a high level language that users are used to dealing with, you need to get to an implementation. The person, the group that provides that path, we want to be those guys for all those groups. It's one of the things of doing the slides right before you come in is you go ahead on the slides. So pretty much what I described here, before. In terms of application, in terms of applications, if you look at the forces driving the industry, driving system level design, the big one is application complexity growing. If you look at the type of applications that people were doing in ASIC 15 years ago, just even simple things that you do on a DSP now were something that required a custom ASIC. Generally, you did your own graphics chips. You didn't even think about doing it on a GPU. Now, if you look at the complexity, Wi-Fi 802.11s and HDTV standards, they're the types of things that are so complex, you can't even think about programming them first in C or lower level language. It's really, you have to get the mathematics right. You really have to get things up at a very high level. And so you want to be working at a level devoid of implementation, something that's easy to understand. Same time, the reasons for doing ASIC are decreasing. It is one of the few things, as I said in the abstract, that's rising faster than the cost of Stanford tuition. Gene France estimated that to do a real custom processor documentation, everything now is over $100 million. Mass cost alone for a single version of an ASIC is over $1 million. And Synopsys and the other guys, because they're getting fewer and fewer customers, keep raising the price of the tools. So the tools are more expensive as well. I mean, maybe I didn't realize it. I think I may have prepared for my future as a hardware designer as an undergrad. Undergraduate degree was actually in chemistry. I was pretty good at physical chemistry. And from what I understand nowadays, in order to be able to do a gate level design, you have to know as much about quantum mechanics as you do about anything else. The tunneling effects and things like that are coming into play. All that says that, ignoring the fact that there's over 100 million gates on a chip and figuring out what to do with 100 million gates is something that's a very difficult thing to do. Says ASICs, there's just fewer and fewer reasons for doing ASICs. Same time, the importance of flexibility and programmability is growing. Nowadays, if you wait till the standard is out before you get a product out, you're too late. The product has to come out before the standard comes out. And so the thing you have to be able to do is modify or adjust things afterwards. If you don't have a programmable solution, you're dead on that. Similarly, the product differentiation, hardware is now commodities. The 100 million gates. You don't make your money by programming those gates better. You make your money by doing things better at the higher level, doing better level algorithms. So you don't want to spend your time mucking with gates. You want to spend your time at the higher level thinking about how to do things at the abstract level. The software is fast enough for most things. So what that says is we're really moving to a level, it's, at least in my mind, the reason I started Catalytic, is that push to higher application levels, those forces that are pushing things up to higher level are coming to the point where it's time for another change or another shift in paradigm. In other words, the forces are now, it's a time where the inefficiencies or the deficiencies of application-specific languages, higher level languages, the benefits are overcoming the cost of using them. And as well, compiler technology is reaching up to the point where you can now get acceptable solutions out of them. So that's what the, high level, that's what all Catalytic is about. Not here as a commercial, this really is a technical talk. And just sort of a brief one, I mean, this is fairly technical, guys, but on the other hand, most of you guys are double E's, so I don't know how familiar you are with the software world. But if you look at sort of the history of development, languages are almost always initially done as interpreters, and then compilers come along later. Just sort of a quick couple of slide introduction to the differences between interpreters and compilers. Basically, an interpreter, coming along the bottom path, is something that it's something that executes as it runs along. In other words, it reads a program, It doesn't go and try and figure out anything about the program. It just looks at the whole program. It just looks at one little segment, addition, subtraction, something like that, and says, how am I going to do that? So what it'll do is it'll read an operation for the program, go in, look at if it says addition, it's got, adding two symbols A and B. It's going to go look up the symbols A, look up the symbols B, look at what their types are, figure out what type of addition it needs to do from that, then go and execute that, and then store the result back, then go and get an operation back and forth. So the type of thing, it's very easy to write quickly. It has a lot of advantages, I'll go into them later, in terms of debugging and things like that. But it's very slow in terms of actually running production code, because you've got all that overhead of doing the lookup and going back and forth as you're going along. Compiler, on the other hand, does a one-time translation. It reads the entire program in, figures out best way to schedule things, figures out as much as it can about it ahead of time, and then spews out an executable that you can run many times. So it has a two-step process as opposed to an interpreter one-step. Reads in, optimizes the program, produces something that you run, and then you run as many times as you want to. Whereas with the interpreter, it's just execute. Whenever you want to fire it up, you execute. There's no separate process. So the advantage of that is you get a binary that runs much, much faster, but you pay some overhead in terms of what you can handle and what you can't handle. So putting that a little bit more specifically, if you look at the code you generate in an interpreter for adding two variables,
that language designers tend to, in the past, tended to put things into the language to make life easy for the compilers on the grounds that efficiency was all, and other people of other persuasions like me got pretty annoyed with it and liked interpreted languages. They're much easier to deal with when you're trying to figure something out.
I agree with that. To put it a different way, same concept. My thesis advisor, when I graduated, two pieces of advice he gave me. Second one was never, ever, ever become involved in language design. We both violated that, and we both regretted it, big time. He got involved in high-performance Fortran. If you go back to System C, I was actually involved in the design of System C. Pardon me?
It didn't mean to play it out.
The first.
The second was not to get involved in language design. What was the first?
First one is, if you're asked any question about parsing, no matter what the question, the correct answer is LALR parsing is the method of choice. But the thing that's been proven over and over and over, to go back to your question, is languages that are designed by committee or that are designed period never work. It's languages that evolve, to meet the user's needs that come in and do that. The closest that came to that was Fortran, but even then they were solving their own needs. If you look in, C versus Ada, Ada was dictated, C evolved, C is the one that won. Verilog versus VHDL. VHDL was dictated, Verilog evolved, Verilog won. So, absolutely, one of the reasons that they are interpreted is first because the successful ones evolve to meet what's needed. And second, you're generally putting in debugging features and things for where you're poking and prodding things, which are much easier to do in an interpreter than a compiler. On the other hand, the counter side of that is until you're able to compile them, they generally meet only limited success. To take the analogy again, Verilog, prior to the existence of Design Compiler and DCS, I think Gateway is like $20, $30 million a year company, something like that. It's did okay, but nothing huge. Design Compiler alone is over 400 million. I assume DCS is now over 200 million a year right now. So it's the interpreters get you going, but it's the compilers that make the money. The reason why you can see right here, if you look at the code that you basically execute or you do in an interpreter, it's basically figuring out everything dynamically. It's figuring out everything as you run. Same thing on the compiler side would just be add, do a simple add, go and do it, it's figured everything else. So that's why you can never implement, or these can never be used as a basis for implementation because there's just way too much overhead. You're looking at running it on a real chip in a real product. Your iPod, if it's running Matlab as an interpreted language on your thing, is not something you'd want to be listening to. Quick summary of the pros and cons. Basically, interpreters are great for debugging. Because one of the things you can do with an interpreter, sitting there while you're running, you can stop it, and you want to change the value of a variable, no problem. Because it's just stored in memory. It's stored in a table someplace. You store it in, you can keep on going. You decide you want to type in a string to evaluate. You want to know what 3 plus 3 is. You can type that in and get that result immediately. Compilers, on the other hand, get speed. They get you speed. They get you, faster execution. You can't do everything in a compiler that you can do in an interpreter. I mean, compilers are sort of the gurus of things. Compilers are going to go in, look at your program, figure out as much about what you're going to do at runtime as it can, generate the best code for that, and then go and take advantage of that. So they want predictability, they want regularity, they want to be able to predict what you're going to do, and then they go and do it. Okay. So getting back to the key part, if you look at Matlab, one of the reasons I spent the time on the interpreters versus compilers is Matlab, as it first came out, was an interpreted language, and if you look at what given the thesis that we're going towards a language that we want to compile, and you look at Matlab, there's really two pieces when it in the early days that it was missing. First was compilation, and that's the big one. Second one is fixed point. Matlab really is designed for mathematicians. And so in its purest form, every variable is a double precision complex variable. It's great for mathematics because it means you don't hit sort of round off or weird error cases. But it also means you got 128 bits per variable. And you got a lot of variables. And again, that's the type of thing, if you're running on an iPod, it would probably be the size of a laptop instead of something you'd be hooking onto your side. So fixed point is sort of the second part that's in there because you don't need the full precision of double precision complex for most things. Most images can be kept in 8 bits. Sound can be done in somewhere between 16 and 24 bits. So what you want to do is give up precision to gain speed and memory and execution efficiency. So the second part is being able to put fixed point in. I'll sort of mention that briefly at times. I assume everyone sort of knows about fixed point here, but just sort of the quick coverage of it is it's using fewer bits than double precision. Generally, there's sort of no exponent, and if you want to, you can add an exponent to widen the range, and it becomes fixed floating point is what it generally gets called. But you have a number of bits. You're using integer instructions. You have a decimal point that you keep track in the middle. It's great for old guys like me where you have to do slide rules, or the ones that use slide rules. If you use slide rules, things you always used to do is have to keep track where the decimal point came out the result. And so fixed point is very easy for those guys. People who have come up with calculators probably have no conception of this type of stuff. But you use integer instructions and have an implicit decimal point, which you shift around. So for instance, if you have 4 bits to the left, 4 bits to the right, and you add to that something that has 5 bits to the left and 3 bits to the right, in terms of total number of significant bits, you actually have 610 that come out. You're keeping track of all of them because you get 1 bit overflow, and you want to keep all the bits around. If you're doing hardware, there's a good chance that that's what you want to keep track of. If you're doing software, you're going to do it, in an 8-bit quantity no matter what. So you want to keep only the 8 most significant bits. So you'd end up being with the 5-3. So when you add, you get the same. When you multiply, you get the sum of the two sides. So you multiply a 1,7 times a 3,5, you'll get a 412. That's probably the key point on that. Because they lose precision, fixed point generally has more complicated treatment of overflow and underflow. Because they're done with integer instructions, and integer instructions are almost done with modulo. You have this annoying thing that when you overflow, you jump around from the most positive number to the most negative number and back, which is sort of a bad thing to have happen going along. So one of the things they tend to put in is saturation arithmetic, so that when you jump over, you stop instead of going around. But again, the key part is trading off precision for memory. And the big point out of this slide is 2 things you need with Matlab to make it an implementation language: the ability to compile it and the ability to get fixed point. Okay. So going through, look at Matlab, I covered it earlier, but if I look at the parts that, at least to me, that make it the language appealing to users, there's 3 aspects of it. One is dynamically typed. In Matlab, you don't declare variables, you just create them. I assign something to a variable, it immediately takes on the type of whatever I assign to it. So, for instance here, if I'm doing one-dimensional things and two-dimensional things, in different cases, so if I want to assign B to be a one-dimensional thing, it's fine. If I want to assign it to be a two-dimensional thing, it's fine as well. I don't declare it. It just becomes whichever one. So at the point at which I get here, where B is used, at that point, the interpreter looks at it and figures out which one it is and goes and does the right thing from there. So I don't have to worry about declaring variables. They just appear. They magically go and, and do what I want them to do. Second part, as I mentioned earlier, is it's a vector language. So instead of just referring to single elements, I can refer to an entire vector at a time. In particular, this is sort of the most clumsy syntax because it's actually referring to the individual elements. But I can use whole variables and whole variables as whole matrices and vectors at the same time. So for instance, here, if I wanted to take the center of a vector and set it to the average of the two elements on either side, I can write a single statement like that that will go into it instead of a for loop for doing it. It's very concise. It makes things look very much like the mathematics involved. Third part is it's polymorphic. It's one of the first job I had when I came out here was with Steve Johnson, for you guys that know him, who is the guy who wrote Yak and Lex and a number of things. He gave one of these colloquiums. You'd have to live in the time to appreciate it. We both came out here and came to work in 1986. And like I said, he had written Yak and Lex, as well as PCC, the first commercial C compiler, portable C compiler. Came and gave a talk at Stanford and mentioned that he had done Yak and Lex, and students popped up and said, gee, you must have made a ton of money from those, which those were at the time working for Bell Labs. That didn't even come into your mind or didn't pop up. The reason I bring that story up, one of the things I didn't realize in terms of the Unix operating system, so the commands there were named very carefully as much as possible, so they only took commands were only 2 characters long. They took one finger from the right hand and one finger from the left so that they were easy to type, saving as much typo. So RM takes one from the right and one from the left. CD kind of screws up because it uses this finger. But that was very much, saving typing was very much a big deal out there. So if you look at another appeal of Matlab, it's also the ability that it can save type as well. If I say A equals B star C, B and C can be matrices, they can be scalars, they can be double precision numbers. It's polymorphic, so I can plug any data type in there and still write it as B star C and cover all those types of things. So it's a very concise way of being able to represent write a lot of operations. So MATLAB's appeal, at least for me, 3 things. It's dynamically typed, it's vector language, it's polymorphic. You look at the challenges of compiling MATLAB, and no surprise, it's it's dynamically typed. Compiler wants to be able to figure out what all these types are and issue code for them. If it has to go and figure out what the types are at runtime, there's no advantage from compiling it. And figuring out those types, there is a reason why languages like C have declarations int. Java, all the languages, there is a reason why they have declarations. One is it makes the job a lot easier for the compiler, but 2, it also avoids user making mistakes as well. Vector languages. Compiling vector languages efficiently is not as straightforward as a lot of people tend to think of it. With vector languages, you get vector temporaries, and vector temporaries take lots of memory. Plus, people always think, that in the 80s, everyone wrote in scalar languages, and if you were taking advantage of vector hardware, it was the job of the compiler to uncover the vector operations and expose them explicitly. And sort of the golden nirvana out there was that if I started with a vector language, it would be very easy to map to vector hardware. And what people found out was that it was exactly wrong. The job of mapping vector languages to vector and scalar hardware is exactly equivalent to the job of mapping sequential languages to vector hardware. So no advantage that comes from that. It's still not something that's been done as well as people would like. And it's polymorphic. It's great to be able to say A equals B star C and mean all those things for the for the person writing it. But the compiler has to figure out which one of those you actually mean and issue code for that. Okay, so we'll take those sort of one at a time. I'm not going to go into any real depth on all this. Today is sort of call it a taste of compilers or whatever. I'll introduce the issues, sort of give you an idea of where the theory out there lies, and leave it for the students who are interested to go off and if they want to become compiler guys or investigate more in the compiler realm of things. So in terms of the dynamic typing, like I said, what compilers really like is for a user to say, this is an int, its length is 32, or it's a 2x2 matrix of ints, or it's a character array, or it's a double precision, or whatever like that. So since MATLAB doesn't require that, what the compiler has to do is be able to infer the types, so figure out what the types are. Worst case is it can turn around and leave that inference until runtime. You can wait till the user is running and then keep a symbol table as it's going along and go and generate code based on that as it's going. But at that point, you've lost all the advantage of compilation. You're basically being an interpreter. So if you look at something like this and you look at B, so with the constant expressions, you can tell what the types are. So for the first assignment to be that that's a 2x1 array or a 1x2 array in MATLAB parlance. And it can actually be an array, a length 2 vector of integers. Second one, it can be complex integers. That I in there is actually imaginary. So it's a 2x2 array that has to be represented as a complex. So compiler can build up those two types there. And then it comes down to reference to B here. You want some mechanism or some way of knowing that those two B's are the type, those are the two types that can reference that. So it's going to be one of those two types. So it can do some dealing with that or have some way of being able to handle that and figure out what the type actually is. So in optimization, there's been an abstraction in compilers for 20 years now called use definition chains or definition use chains. It's basically a mechanism for hooking up all the definitions to the uses. So at that point, what you can do is come in, look at the use of B, come back to that, find all the definitions that can reach that, see what those types are, and then assign a type here that fits or is appropriate given those two things. So here, because one is an integer vector and the other is a 2x2 imaginary array, what you want to be able to do is assign a variable array of imaginary numbers here. I mean, that's the closest, that's the smallest sort of type that will handle both that comes in on that. So that's the type you'd want to assign. And then you go on from there, and it sort of causes some bloat in the types because it means you're less efficient than you'd like to be when you have just the 1, 0 coming in, which can be done as an integer. But at least you've got something that handles everything, and it comes around and accounts for that. Okay, so that process that I just described of taking one type coming in here and another type coming in there and figuring out what the smallest type that can handle the two is something that's fits a paradigm that's well in compiler optimization theory. Basically, it's coming in the format of a lattice. The place where you tend to see lattices most are in constant propagations. I mean, you think about it, propagating types, propagating constants. They're pretty much exactly the same thing. What you want to do, a constant, if I know all the uses, all the definitions that reach a use are the same constant value, then I can go and reference that. If I know two of them are different, then I know I can't use a constant there. And if I know nothing about any of them, then it sort of all give up. So same thing with types. Basically, the framework or the theory underlying it is that you have a lattice here of types, and you can move up to points where you know where you are in the lattice. So if you start in, if there's nothing reaching, if you don't have any uses reaching, any definitions reaching use, you know absolutely nothing about the type. You can't make any inferences whatsoever. If you have one definition that comes in reaching it that's a character, and then you have other definitions that you don't know what they are, you know at least that it can be a character. But if you have two coming in, one character and one logical, let's choose a better one. So if you have one coming in that's an integer and one that's a double, then you know you can represent it as a double. I mean, a double will account for all the things that are integer. So you can do it as a double, or you might want to do it as some sort of combination of int and double around as well, because you may want to try to preserve the integer characteristics when you can. The example we gave before, complex and double, you can definitely do those as complex. So what happened is you add in more and more definitions, then you can move up points of the lattice. Worst case, you go up to one that has multiple types that you can't go and account for. In Matlab, that's no problem because everything can be done as double precision complex in Matlab. That's sort of the ultimate type. So this lattice doesn't represent Matlab, but what it means is worst case, you do everything as double complex. But ideally, you end up at some point lower in the lattice where you can go and accommodate for things. So things with lattice, the nice part about having a lattice framework is so long as the lattice is bounded, finite, and monotonic. In other words, as you only move in one direction, then you know your problem is going to converge. I mean, you just keep adding in more and more things, and at some point you'll stop at a point on the lattice. You won't just keep going. But it's got to be bounded because otherwise things will keep on going. So if you look at Matlab without fixed point, it's very easy to show that the lattice is finite, bounded, and monotonic. Fixed point is a different matter. I mean, so anyone see what the problem is with fixed point, or does fixed point meet a bounded lattice?
Have arbitrarily different places for the fixed point. So every fixed point representation is itself a member of the lattice. Right.
Or even more so, I mean, we'll skip on past that. Here's the one where you start hitting problems. So, I mean, this actually is a real example. This is the power method for computing eigenvalues. But, what you have here is a loop. And so you have a type feeding in on itself. And if you remember, I described every time you multiply two fixed point numbers, they grow in size. So in this case, you happen to know the loop only goes 2 times. But if you don't know how many times the loop grows, then that lattice, there's no bound on the lattice. The number will keep growing bigger and bigger and bigger, the number of digits in it. And so the lattice is no longer bounded. You're no longer guaranteed things will converge. And you reach a point where, the theory all falls apart. Is that a question?
Yeah. This is particularly bad when the variable that's growing is invisible, that it's an intermediate that doesn't explicitly have a name. Do you take responsibility for preventing overflow in hidden temporaries, or is that somehow the user's responsibility, or what?
Well, so it's exactly the same way we work around this. So we give the user a mode where he can control where the sizes are. If he says he wants the sizes to grow unbounded, then we're not going to be able to compile it. But if he puts some bound on it or somehow limits the bounds on it, we take care of that. We never restrict the precision without the user's explicit consent. Okay. So I mean, that actually, look at the sort of 2 things here. I mean, first, filling in the use definition chains. You can start to see it. You can see the real problem is the loop back around here. U feeds in here and then back around. So if you've got some growth there, it's going to grow unbounded. So the 2 problems are loops and fixed point. And the solution is, it's sort of another thing I learned from my thesis advisor. If you don't know the solution to a problem, redefine the problem so you can fit it to one where you can find the solution. So the thing to do is restrict the programs that you accept so that the lattice is always bounded. And basically that means you have to have variables so they have one and only one type. You don't let them come around. You force them to converge to a fixed point when you're iterating. And with that, you bound all the operations in size. And it's not a very onerous restriction. Generally, that's what people want. Sort of another way of looking at it, variables always take on different values. Variables rarely take on different types. If you have a variable representing temperature, it's certainly going to have a different number of degrees as it goes along, but it's never going to take on foot-pounds or furlongs per light year, I guess, if we used to do it when we were doing physics problems. It's always going to take on the unit of temperature, so the type will always pretty much be the same. Okay. Just sort of one other thing. I guess the equivalent question to, or the equivalent response to LAOR in 1980 is, method of doing data flow or of computing nowadays. If you're asked what the method of doing data flow is, the correct response is static single assignment, or SSA. So no compiler talk was, sort of complete without at least mentioning SSA. And it's actually important here because we come back to the points, the join points I was talking about. It turns out that SSA gives us exactly those, or tells exactly what you want. So SSA, for those of you, who don't do it, you come back to the thing we showed here. You start seeing the number of edges growing and identifying the join points and all of that. There's a problem, like I said. You come in, the initial type of U up there, you come into the first use, you can't propagate that type on pass until you know what the type is down here. But you can't get that type without propagating it down. So it's a problem that SSA was designed for. What it does is introduce new assignments. So a variable only takes on one type. You create new variables in terms of getting new types. So we come in, you'll see there's a phi function around here. You start out with initial U. It can reach the, the first statement there. At that point, there's 2 U's that can reach there, so we put a new U in, a U1 in for the quantities there. It can reach the second one. U2 then reaches, the third one, and then U3 can reaches back. And so in hardware terms, it's a mux. In software terms, it's a phi function. In railroad terms, it's a switch. What you put is a switch there that selects among the types. Unless you come in from there and, unless you from that exactly identify the points where types can join or change. The phi function is exactly the points where 2 types come in and change, and you have to do the joining on those. This actually really was, the other thing you learn as you get older is that the problems and the solutions are the same sort of across all spaces. They just have different names for them. This actually was, fairly significant discovery in compiler theory, even though in other areas it's sort of been around for a long time. I mean, the analogy I use here, so these, since I'm sure no one knows what these are towns in North Louisiana. And if you look at, sort of where things grew up, it's actually towns around where I grew up. If you look at sort of initial laying out of a railroad, the way compiler guys initially did data flow was like this. you want to get things from Antioch to Hilly, or or from Vienna to Homer. There were some real jokers in the early days of Louisiana. The fact that a town's named Homer or Sparta means there were some Greeks running around. And Vienna had 3 people in it when I left. I think it's probably 2 now because the pastor left. But the way compiler did things was make a connection from every possible one that you can do it, sort of an n-squared type of connection, which is really, really inefficient when you try and go and do it. Smart thing they did with the railroad is they come in and put one town, one switch in between, and then you come in and switch from that and go to the others. So that town was actually where I grew up, Ruston. And there you end up with a linear number of things instead of a quadratic. So that's all simple and easy to understand. The interesting part of this, the part where compilers really did make a great advance, is figuring out where to put those switches in. That, if you think about it, is a very hard problem because you want to put the switches in a minimal number of optimal places. And so that's the interesting part from the compiler point of view. I'll just reference you to the paper, probably the best paper on it if you want to go and read it. And that will get you, that's a very complicated problem I won't even begin to go into here. Okay, so second problem, vector languages or vector semantics. So when I say a statement, the semantics of vector statements are simultaneous. So when I write a statement that takes the chunk of the middle, and sets a chunk and sets it to the average of the 2 around it, what that's really saying is I grab those 2 vector chunks at once, combine them, and store them all as one operation. So it means I go and grab the first chunk, pull it down, grab the second chunk, pull it down, and I've got the combined result coming in. So the thing that threw everyone off when in the early days when they were looking and saying, oh, this, going from vector to sequential is easy. All I have to do is just write a do loop around it. If you look at writing a do loop around this, you'll see you get different behavior. So we come in, so we do a do loop around the first one. So take the, this element and this element, combine them, put them here. Then we want to move on down and compute this element. Compute this element, we want to take this one and add them together. But you can see we screwed up because the value we want for this one is the old one, not the new one. And so if we do this, we'll get different answers. I mean, that's the fundamental part of vector operations and where the scheduling and handling them is hard, is that you can't overwrite. You have to make sure that you're putting something, taking the old values in before you put the new values on top of them to make sure the semantics are the same. So one way of doing that, or thinking about it, is just use a temporary. So, okay, if I do all the operations to a temporary and then copy them over, then I will take it, then I won't have that problem. But then I've got the problem of inefficient execution because that temporary is going to be a vector temporary, not a scalar temporary. And it's not something that you get for free in a register. That can end up being a lot of memory. And so it ends up taking a lot more space than you'd want to. Actually comes down to sort of a third part, sort of a third related thing here is what I call horizontal versus vertical compilation. If you look at the way an interpreter executes vector operations, it does what I call horizontal type of things. It's going across the page and then down. So if you look at something like adding 2 vectors and dividing it by 2, it's going to sweep all the way across, do all of those, and then move down to the second set and do those. Very easy to do, very easy to schedule. Absolutely abysmal in terms of memory reuse. I mean, here you're fetching A and B all the way through the first time, then coming back and fetching them again. That second fetch is totally useless. What you really would like to do is instead schedule the 2 together. So that if you've got a smart compiler, it will know that these 2 fetches don't have to be done. They can be kept in registers that have gone across there. Okay. So that's, this is really the way you want to schedule things and do things. In doing this, there's a common theme among all 3 of these. And the common theme is being able to detect when a memory reference on one iteration of a loop accesses a location that's also referenced by another location, by another iteration of the loop. That's what comes across. If that doesn't happen, then we know we can schedule things in terms of vector operations and scalar operations. They'll be the same thing. In terms of temps, we can actually know we can fuse the loops back, so that we did, sort of equivalent condition there. In terms of horizontal versus vertical compilation or execution, we know we can shove things together horizontally when we aren't violating that type of constraint when we shove them together. So that's the key thing there's sort of two facts about that. I mean, first, if you're hardware guys, you've seen this all before, write after write, write after read. There's sort of one way you can turn around and get it. You know, there's the type of access, and then there's the actual nature of, you know, the actual access itself. So the abstraction that's built on that is data dependence. I mean, what we're going to do is define an abstraction, a dependence graph that sits on the program, such that two iterations of a statement are dependent if there's some memory access conflict that has to be observed. It has to be kept for the memory for the program to be correct. So the idea there, you know, if you take a program in either sequential or vector execution, there's a total ordering on the number of on the iterations in the way in which you execute, you know, set by scalar. Scalar execution, say, do this one, do this one, do this one, do this one. In fact, those aren't, you don't have to do those. That's not the only thing that will meet the correct results. There's only a subset of those that absolutely have to be met. So what we want to do is define the essential orderings with the dependence graph. At that point, we've got all the execution constraints that have to be met. So we can reorder the program however we want, so long as we don't violate those. And we end up having a, you know, the correctness is preserved or kept out of that. So that's one aspect of data dependence. Counter aspect, we want to be able to reuse memory, or, you know, avoid fetching memory when we've already got it there. Got a dependence between two statements, means they're accessing the same memory location, or maybe accessing the same memory location. So it probably means there are two things we want to keep together, because that, you know, there's potential for memory use between them. Okay. So this will be a very short, you know, foray into the, you know, theory of the data dependence. So we look at how do you formulate that mathematically? How do you want to put data dependence such that you know, detect whether you've got dependence between two statements? We look at the subscripts. You know, take a variable x. The subscript function for that is f of I. So if the function there is, you know, 3i plus 2, then f is 3i plus 2. You know, g of I. Then there's going to be a dependence between those two only when there exists I1 and I2, such that the functions are equal. And because we want it to be across loop iterations, you know, the second one has to come after the first one. And then it has to be within the execution of the loop. You're going to have a loop around it. So if it occurs outside the bounds of the loop, then it doesn't matter. That's mathematically, you know, a better way of seeing it is graphically. You know, we have one loop, you know, one loop variable I1, another loop variable I2. And we have these points on which we're looking at the function, f of I1 minus g of I2. Okay, and those points are actually chosen, you know, directly. There's a line up through there, doesn't show very well, but this line is always this one plus 1. So if on the second iteration, if on G2, G2 is equal to f of 1, then there's a dependence, because that means on the second iteration of the loop, that the second one is accessing one stored by the first one, and so on. On the other hand, if you turn it around, if on the second iteration of this one, it accesses something that was fetched on the first iteration of this one, there's no dependence, because this one has sort of gone on, you know, it's happened too late, which is why this half of the curve is missing. So this is the key part here, you know, is we have a set of, you know, here's a set of discrete points, and here's an equation. And so if that equation has a solution on any of those discrete points, then we've got a dependence. If it doesn't, we don't. Okay. So, any mathematicians in here? Is that an easy thing or a hard thing? It's a hard thing. You know, you're looking at discrete points. You know, integer programming is about the only way you can do it. So that's a very expensive type of thing and very hard to do in general. So if you're looking to show that there is a dependence, if you're looking to actually solve that equation, in general, it's a very difficult thing. On the other hand, we don't want dependencies. What we want to do is that there not to be dependencies. So what we want to be able to do is show that there are no solutions to the equation. So then we start coming in and getting to a range where it's very, you know, easier, more to deal with. Particularly since almost all subscript functions tend to be affine. They're linear functions of loop variable. So when you get linear, you can start dealing with things. So got an equation, f of I equals f of I1 equals g of I2. Linear, you know, they're both linear over loop variables. We have the set of discrete points. How can we show that there are no solutions in that space? No mathematicians in the bunch? Okay. Well, first one, so if the GCDs don't match. So if one of the functions is 3i plus 1, and the second one is 3i plus 2, so the GCD, so 3i plus 1, 3i plus 2, it's always going to be jumping so that you never reach. So that's one that takes advantage of the discreteness of what you're looking at, but totally ignores the bounds because, I mean, they're never equal anywhere or everywhere. Second one is just sort of being able to do simple linear algebra constraints. If one is I plus 1 and one is I plus 2, you know, again, it's always going to be ahead. They do overlap, but it's always ahead, so it can only go in one direction. But the third one, you know, actually is the most interesting one and the most convenient one. Because what makes it so hard is dealing over the discrete space. It's one of the things, you know, like I said, being a chemistry major in undergrad, one of the things you learn is with quantum mechanics. It's all the discreteness that happens. It's when things jump from place to place and you don't know what's going on that gives you the problems. Same thing in this type of thing. It's the discreteness of the domain space that's the hard part. If you turn around and relax that discreteness and let it become continuous, then it's actually sort of simple calculus. In other words, if we go back to this graph, and instead of just having it on those points, have it be over that region, then it becomes a very simple one because what you can do is use the intermediate value theorem of calculus. So if the minimum of that function is always greater than 0, it's over that region, and it's a continuous function. The maximum is always less than 0, then you know it's never equal to 0. So if it doesn't have any real solutions, you know it doesn't have any integer solutions. So that's the one that can come in and do with the bounds. What works out of that is a really hairy inequality that I won't put up, but it's due to Uptal Banerjee, and it's actually a very, you know, it's one of the most efficient tests there is out there. So that's the basis. You know, it's all that dependent stuff. It's basis of a whole bunch of optimizations. You know, the key ones being here, ability to fuse loops, block loops, interchange loops, being able to strip loops to different lengths, ability to reverse loops. You know, basically anything you want to do with loops all comes around from that type of work. So it's really handy stuff to do. You got to put at least one plug in. You know, co-authored a book. You know, so if you really want to learn about this stuff, so for future reference, you know, this is a place to go and go. If you don't know it already, the absolutely worst way to make money is to write a book. You know, particularly write one that's only for graduate level classes. The guys who are smart are the Samuels and Apostles, and you know, the guys who go for undergrads. There are worse ways. They're probably not worse paying ways. Okay, so we've covered 2 of the 3, you know, and we've gotten through the Iraq of the 3, I guess, you know, and sort of coming down with polymorphism being the last one. You know, so we have the statement A equals B times C. I want to be able to figure out, you know, user can mean lots and lots of things with that. It can be vector times vector, it can be dot product, it can be fixed point times fixed point, integer times double. He wants it to be all of those, and we need to figure out what are the ways out of that, you know, what's he really mean? What's he hunting for there? So our approach is we go and generate code for all of them, and then basically we gather as much information and aggressively propagate it to eliminate the ones we know don't fit coming around out of that. So, I mean, the real key part is getting the information there and taking advantage of it. But just to give you sort of a quick example of what I'm talking about. Now, take an example here, users coming in and doing 2 matrix multiplies. In one case, he's multiplying 2 real matrices, and the second one he's doing 2 complex matrices. So in order to be able to handle that, you know, here's the function call here. The MB real, the MB complex are just saying what the types of matrices are. In order to be able to handle that, for the complex one, we actually have to generate a lot more code than you initially would think of or turn around, because if it's 2 scalars that we want to multiply at one time, the scalar times a matrix, which is the second case, we have to go and do it a different way. If it's a matrix times a matrix, we have to go and generate code a third way. So we have to generate all of those. You know, the part the user is usually used to seeing is these 3 loops right here that comes around and does that. Similarly, we'll split it. You know, we also have to generate code for the real version. It comes around and does exactly the same thing for the real loops. It's doing real operations instead of complex, because we don't want to accumulate the intermediate products of the imaginaries if we don't have to. Okay. So we've got it here. Here's the case of A scalar, case of B scalar, and then where they're both the general So the key part, the place where sort of the future research comes in is how do we get more information about what the user intends? How do we, if we can find out more about what the user really wants there, then we can generate better code and get rid of the cases that aren't there. So if you can come in, for instance, and tell us either through the size facility here or assertions, the sizes of the matrix, or even the fact that some of the sizes are greater than 1 or 0, then we can go and do a much better job. In fact, what we'll do, in this case, is we get rid of all the code. We're able to propagate forward the information that the scalar case doesn't account for. It's not necessary. And so we only generate what he expects to see out of that. So the idea there is that what we're going to be able to do is have a high-level representation that lets you generate any sort of number of things that you want to, that's fully polymorphic. And then we come around and take advantage of, we optimize and get context-specific code by gathering information and propagating that and take advantage of it. Okay. So putting it all together, sort of the one part of the thing, we come around and giving you an example here on a processor and showing the type of code that we generate for it, and sort of compare it to what you'd expect for human code. What we've got over here is sort of very simple. It's adding 2 fixed point vectors that are both 16-bit long. They're 100 length. First one is adding 2, adding, subtracting 2, and then taking the product of combinations of them. So it's Matlab over here. Over here is the code that we generate. Sort of the key features on it. We're able to take advantage of specific features that the compiler knows about on the other side. Restrict is a really important part of the C standard for the compilers that know about it, because without it, basically, you can't do any sort of optimization on anything with pointers. When you restrict it and say the pointers don't overlap, then you can do a much better job. So one of the things we can do is analyze the pointers and guarantee that they don't overlap. Take advantage of intrinsic operations. In this particular architecture, there's operation for doing saturated multiplies of short bits. So we can come in and take advantage of that and issue a call to the intrinsics operation that will do not only the saturated multiply directly, but also doing it 2 at a time because it's working on short vectors. Able to take advantage of alignment and do vector aligned loads. So, in other words, this particular architecture here, you look above, it's actually loading up 2 operands at a time and using the memory locate loads for doing that. Able to take advantage of vector operations. One of the things you get from Matlab is you start with vector operations, so you don't have to go and uncover them. You can take advantage of them and strip down to them. So it's a big win, because virtually everything out there is getting short vectors nowadays. Everything from Altivec, Intel architectures, everything has short vector operations at the fixed point. That's really important. And then we're able to rearrange loops. If you look at these carefully, these loops around the statements are all length 100. If you look at the way we generated it, we generated one loop all by itself, doing the addition in a loop that goes 2 at a time, because there's an intrinsic that will do 2 of those at a time. Then we generated the 3 loops all together fused inside of one vertical loop type of thing, which goes with a different stride because there's not vector operations for this. They're just simply scalar ones. But not only do we do that, but we're able to keep a temporary between the 2, so we aren't reloading and taking advantage back and forth of memory. So if you look at the code that, here's Matlab code that in the abstract can be doing lots of different things. When we come down to the code we generate for it, it's actually very reasonable code that would not be that bad at all. I started out by quoting Hoare, turn around and sort of quote him again at the end. There's 2 ways of designing software. One is to make it so simple that there are obviously no bugs. The other is to make it so complex that it's not obvious that there are any bugs, whatever. If you look at where we're moving in terms of the future, the complexity is getting there whether we like it or not. It is getting that complex. So the key thing in order to be successful and continue moving forward at the rate at which we've been doing is to be able to design things so the simplicity, so things are understood. We can look and see the important parts and not have to look at the unimportant parts. So a big picture, again in terms of catalytic, big picture is things are moving to more higher level languages. Things are going to get more complex. We've got to be able to manage the complexity. Going back to the chemistry background again, it's probably one of the few things that have the levels of complexity we tend to think about. If you look at DNA and trying to understand proteins at the level of hydrogen atoms and carbon atoms, you would go nuts very quickly. It's one of the things I remember, the two things for DNA is Clark Gable and Ursula Andress. Clark Gable is cytidine, guanine. It's things that has 3 hydrogen bonds between them. Ursula Andress is uracil and adenosine. It has 2 hydrogen bonds between them. That's all you need to know for understanding DNA, are those 2 things right there. But if you try to take that down to the level of quantum mechanics or understanding individual hydrogen atoms, you'd go nuts. You have to do the same thing in languages if we're going to be able to do complexity at the level at which we're trying to do things. Compiler optimization is the critical part for that. If you go back, we've had some really neat high-level languages since the early 60s. One of the ones my thesis advisor worked on was one called SETL in the 70s, Set Theoretic Language. Really cool language. You could do all sorts of things with sets. I mean, you turn around and say, I want a sorted set. It would be able to infer that and do that automatically. Unfortunately, the way it did it, it would generate the power set of all possible subsets of that set and then choose the one that fit the sorted criteria. So it wasn't real efficient, but it was really cool. And then the gaining information, the key parts looking ahead is how do we get information from the user about how he wants his actual application to go or be. Okay. So, I mean, language really does impact the way we think about problems. I mean, one example I always like, there's several examples I like to use, but here's sort of the one closing up. Everyone know what this integral is? Yeah, I mean, it's really important. This is probability distribution function. You guys are Stanford guys. You guys know how to evaluate that in closed form? Yeah. Okay. Okay. Turns out you can't, I mean, there is no closed form solution for that. I mean, if you go and try to solve that directly. Yeah. I mean, it's actually, and looking at it that way in Cartesian coordinates, there is no closed form solution. I mean, you can't go and solve that. On the other hand, if you turn around and transform it to polar coordinates, it's in fact very easy to solve. I mean, even I can go and still integrate that. And in fact, that's the way that's why you come up and getting a square root of pi over 2, is you transform and look at it from this coordinate system. I mean, so again, the way we talk about things or the way we phrase things can make it very easy or very hard to understand them. I mean, another example is relativity. If you look at Maxwell's equations in terms of integrals, which is the way engineers always look at them, you'd never infer from that anything about relativity at all. If you look at them in their more natural form, there's doing the integral with a little circle in it. It's very hard to figure out things. If you look at them in divs and grads and c's, it falls out that from that there's a wave that travels at a constant speed irrespective of the frame of reference. And with just a little bit more math out of that, you've got relativity. The way we think about things, the language, how we view things is really critical to making progress. Okay, that's all I had. Good time for questions.
Question?
Target for the application, target machine for your...
Well, right now the big one is actually the Intel, because most people are running, so my background is both chronologic, which is VCS, which did simulation acceleration, as well as working at Synopsys, which did sign compiler synthesis. One of the nice things about this is you can do both with the same thing. So one of the big things we do is actually speed up simulation as well as generating targets. So the Intel is by far and away the big one. There are others as well.
First one is, what are you going to do about modern machines? When the number of cores gets to be fairly large, the need is going to be to partition processing across each of the cores so that you get performance. Most of the optimizations that you've described have an implicit assumption of both a single processor and a memory which is accessed in a reasonable, rational way and not in parallel. And what's the chance that we'll be able to compile in something like Matlab into that kind of a multi-core environment?
So I mentioned this stuff called dependence analysis, and there were two key parts of dependence analysis. First part was that it summarized all the execution orderings that you had to obey. And so once you had those execution orderings, any other execution that meets that, do a topological sort on that, anything that meets that topological sort works. So, I mean, that includes parallel. I mean, parallel ordering, so long as it meets those dependencies, can do that. You know, so if you can get those precise, that's sort of one part of yours, that there is a basis. I'm not claiming I've solved all these problems. You know, I did my thesis in 1983. I'd be like Steve Johnson. I'd be rich and retired, or more like Bill Gates would be the other. You know, so that's one aspect of that, the execution aspect. The other aspect, you know, how to, you know, no matter how, so a programmer, no matter how he, you know, no matter what, history has absolutely proven that shared memory paradigms is the only way programmers can understand for programming machines. And it's also proven that hardware designers can only implement them using distributed memory or something that eventually becomes distributed underneath. You know, the second aspect of dependence was that if you've got a dependence between two things, it means there's a common memory or potential of common memory access, so that you want to rearrange the things so that you get those memory accesses where they're on the same processor things. So I don't have an answer, but I do have the fundamental belief that if there is an answer, dependence is going to be at the basis of it, and it will be a key part of it. You know, it's part one. And part two, you know, so MATLAB, linear algebra types of things, you know, the key part for compilers is being able to predict, you know, have a regular computation where you can predict what it's going to do next so you can go and schedule it. You don't get more regular than this stuff. I mean, there you can look at it, understand it, and, you know, and predict the way. Whereas things like an FFT or, you know, random C programs, who knows what they're going to do.
I'm like you, probably a gray hair if they had hair. But a number of people worked in a slightly different environment, but somewhat similar. They were trying to compile APL, which is another vector language. Requires a interesting key set. Yeah. But basically their approach to the polymorphism was a little different. They deferred compilation of things rather than trying to do a huge static analysis until something was required, and then compiled that and kept a cache of these small little snippets of compiled code. And I'm wondering what the trade-off between these two is.
Well, I mean, a higher or more modern version of that, JIT compilers versus real compilers. I mean, basically, they had the first JIT. You know, it's just a bigger thing. So, JIT compilers can do amazing things, but you know, if you want to generate a real application that's running on an embedded processor, or, you know, something that's out there, you can't afford the uncertainty of, you know, dynamically compiling it, you know, coming along and doing things. And more than that, you want to get the full, you know, you want to come in and do optimizations that you can't even think about doing while you're, you know, while you're executing.
Okay, but if this is caching code and you have full coverage, then doesn't the code that remains after running your test suite actually provide all possible options that are executed?
If your test suite covers all possible executions that you can have at runtime.
Would it not?
Maybe you've worked on different projects. So you worked for HAL, if I remember right. That was, so
it's an interesting problem.
Yeah. I mean, and it's, you know, if you go back to this, you know, at the point at which I started Catalytic, it was before MathWorks has a JIT compiler out now. When I started Catalytic, it was before the JIT compiler had come out. And there, I mean, you know, because there's a little bit being, first thing people always benchmark machines on is matrix multiply, because that can really tell you sort of how good a compiler is. So first thing I did in starting Catalytic was write what matrix multiply by hand, and, you know, compiled it against the MathWorks. You know, expected a speed up factor of like 100, 200. You know, ran it. Mine ran in 5 seconds. Theirs ran in 3 seconds. So I was going, uh-oh, I mean, have I quit my job? But then I thought about it and it actually made sense. It's one of the challenges of this stuff. I mean, so doing it that way, I coded the matrix multiply as a single operator. And you think about the typical overhead of interpreters that's going back and forth. But 100 by 100 matrix multiply, when it's a single operator, you just dive once into a hand-coded routine, execute the entire matrix multiply, and come back. So I was looking at my C code versus hand-coded, you know, assembly code, and, you know, so expect loop. So then I wrote the matrix multiply as 3 loops in Matlab, and after 24 hours, you know, I got tired of waiting for it to come back. But it's actually one of the challenges in this direction is with vector operations, you don't get the big kick that you get over, most interpreted things. And with the JIT compiler, I mean, it's one of the reasons they came out with the JIT compiler is they had some things where it's just abysmal.
Discover an FFT computation in somebody's code and transform it to a call?
We can. We don't do that now. I mean, there's... so, I mean, being academics, you don't always sort of see the uglier side of benchmarks. I still, one of the reason this comes to mind, one person, LINPACK benchmark in the 80s was like key for your performance. I mean, that was key as to metrics and things. And the way I heard one person describe, someone's performance on LINPACK is an asymptote, because it's the vendors themselves who are going to do it. It's the number that you're guaranteed, no matter what you do as a user, you will never exceed that performance on LINPACK. Because in particular, one company, I guess I won't name them, but they actually had M4 macros that ran ahead of their compiler that recognized the comments in the LINPACK benchmark. And when it saw those comments, went and generated code to do it, assembly coded types of things.
Yeah, something else.
Yeah, but so coming around, there's always more things you can do in compilers. FFT is one of those things that isn't regular, like a compiler can understand. But at the level at which you represent it is the type of thing you can recognize and do pattern matching for it very easily if you want to. It's one of the things at some point probably will add, but we don't do that right now. Yeah.
Actually, the guy who had the benchmark which detected that kind of thinking in benchmarks spoke in this class some years ago.
Oh, really?
Yeah, he had a benchmark which consisted of things like common benchmark groups plus versions of them which have been slightly modified to do something slightly different.
Mm-hmm.
And he had graphs showing how well the standard version did versus the slightly permuted one.
Uh-huh.
But what was really striking was there were some compilers where they saw the slightly permuted one, misrecognized it as the original, and generated the wrong code.
Yeah.
Actually, the nullstone.
Oh, no, sorry, Chris, yeah, I can't remember his last name. No, there's that one, another one that, so in the early 90s, when the first specs came out, spec benchmarks, matrix multiply was one of the ones that's on there. And the reason people do matrix multiply is, I mean, you can do it, make a factor of 100x difference, on it. So Cook and Associates was a small company out of Illinois that has had sort of modest success so far. But they reached a point where every company, HP, Sun, every company out there bought a copy of their product because they would recognize the matrix multiply inside the spec benchmark and turn around and generate the correctly blocked code for it. So why it wouldn't, it may or may not run on anything else, but it would give them a factor of 100x speed up on matrix multiply in the spec benchmarks, which would kick numbers up pretty dramatically.
Anybody else? Any other questions?
Well, when I was working in this area in the late 80s and 90s, I think one of the things that occurred to me is that we're not really going to be able to use static programs really anymore. And it turned out I ran into Bill Wolf and I went to Tartan Laboratories. And they tossed out static programs entirely. And Bill wrote program generators made out of Icon in order to basically test, since you had mentioned Ada compilers. Ada compilers have not disappeared.
Yeah.
I defy you to get on an airplane right now written in C.
I would
They're
scare,
all running.
I would
They're all
be
running
scared to
Ada.
death of doing it.
Yeah.
I mean, don't take me the wrong way, but if you look at, if you look at commercial success of what most users will grab, Ada versus C, when they aren't constrained by things like safety, it's C. Same with VHDL and Verilog.
Actually, it's the thinking of two different communities. The aerospace community for which I work, they have very, very backward ideas about a lot of things. So.
I wouldn't call it backward. I mean,
no, I'd call it. In the past, I would have been kind. No, they're truly backward.
Well, I mean, the way I heard it, so 6 Sigma is the normal thing you take as safety consideration. 6 Sigma in the aerospace industry means there's 2 plane crashes a day. And given that I fly a fair amount, I appreciate the backward thinking.
Their comment is, checklists for the blood. And, most computer people, Andy Michael, very early on at the University of Maryland, well, Ada is designed to kill people. Right? That's the whole point.
Yeah. Okay.
So you said you worked for, I guess, Synopsys and such. Have you thought about taking this and actually using this to generate an application-specific processor? For instance, let's say you had some algorithm and you wanted to optimize that algorithm for as fast as possible.
I mean, it's safe to say there's almost nothing involving Matlab in what you come out with that I haven't at least thought about.
Okay.
But you know, I am a capitalist at heart, and I go where the money is first.
Yeah.
And then we look at the things out there. I mean, if you look at where the money is right now, I mean, it's general processors, embedded processors, you know, that type of space. I mean, you know, part of what, well, it's not one of those things, you know, I should say publicly. You know, there's one part here we're trying to do something which has been done very rarely before. That's make a compiler company successful. I rarely use the phrase compiler associated with the company because that's like anathema to, you know, VCs and stuff like that. Even though we're actually in a room named after the first guy to make a compiler company successful. You know, Microsoft started off as a compiler company, and there have been others out there as well, but not. You know, it's a tough space just from a lot of, you know, historical points of view, if nothing else. So I have thought about it, but not, you know, not a place we're going at right now.
Question: do you just work with Matlab or any other type of programming languages as well?
I mean, so Matlab, I mean, if, you know, sort of going back to the point earlier, in my mind, the signal processing guys are well ahead of everyone out there. I mean, it is a universal methodology that people start with Matlab and go on down. You know, the thing I've learned is I don't want to be in the language design. I want to come in after they've accepted the language and compile it afterwards. Matlab is a clear winner. There's lots of other spaces out there, but you know, the winners aren't there yet.
Interesting, the comment about the aerospace industry. Matlab is being used mainly by aerospace and automotive industry for a variety of reasons, okay? And are you going in your compiler work outside of the vectorization, or you're dealing, for example, with there is a state flow in the Matlab. There are a number of packages. It's a huge environment to work with, or you are strictly limiting yourself to .m type files.
You know, again, I'm a capitalist, you know, and one who optimizes as well. You know, so the part where, you know, at least the big bucks and the big spaces is on Matlab. You know, there was Matlab the language, Matlab the libraries, and Matlab the, you know, the GUI or the visualization. You know, like the Simulink and all the other things.
This and that and.
So number one, focus on Matlab. I mean, number two, you know, a little bit of a religious bias here, so I'll preface it, you know, with saying that if you look at the history of things, text-based, you know, language-based approaches versus graphical-based approaches, you know, language is eventually won out. It's once you start getting more and more complex, it gets very hard to represent things in a graphical viewpoint. So if you go back to the 80s, you know, there was schematic entry or schematic capture, and then there was, you know, Synopsys came along with RTL, and the language came and took over. So I'm you know, just from a personal point of view, I'm a big believer in the language base, because if you look at the complexity, you know, trying to draw a diagram that represents the complexity is very difficult type of thing to do, you know, once it gets to be very complex.
They are not particularly complex or diverse, okay? They can all be represented by language. For example, finite state machine can be represented textual language. It doesn't have to have the circles.
Yeah, I mean, you know, there's one part, you know, so the nice part of that approach, you know, compiler techniques, all the types of things we talked about are great for data computations. You know, Matlab as a language sucks for control computations. I mean, there's no reason for, you know, for doing it. Whereas the graphical approaches are great for the control types of things. You know, so you know, the data things are the things I know how to do, and the things we really focus on. And you know, who wins out or what will win out in the control space, you know, is a different matter.
With that, I think we'll cut it off. I'm certainly ready to answer questions down here from those who want to continue. Thank you very much. Andy, we'll see you next week.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.